Life.
Okay.
Wait, life.
All right. So, hello and welcome everyone. On this pleasant evening, it is my privilege to welcome all of you to this wonderful interaction. We at Space are constantly working towards the development of science and astronomy in India, aiming to create a scientifically aware society and contribute to the technological and social development of the country. Space is providing services and products in area of astronomy and space sciences to schools, colleges, NGOs, corporations, and individuals. Our trademark has always been innovation, passion, and total commitment to spread knowledge of astronomy and space sciences among the masses. So that is why every project we conduct is an opportunity for us as well as whoever participates in it to communicate our belief in developing scientific temperament in people, especially students, to create intelligent and analytical global community. And so here we are today, and I, Aditya Jaiswal, on behalf of whole team of Space, with immense pleasure in this wonderful evening, welcome our guest and a brilliant mind here with a round of applause, I'm sure, Dr. Christos Markou. Right? Dr. Christos, who is the director of Institute of Nuclear and Particle Physics of NCSR Demokritos in Athens, Greece, as well as the chairman of KM3Net Institution Board, member of the Resources Review Board and Publication Committee, and he as well as being the Greek delegate of the KM3Net European Research Infrastructure Consortium. He is also an experimental physicist, and his fields of expertise are astrophysics, particle physics, instrumentation, distribution computing, and data analysis, as well as signal processing. He has participated in several high-energy particle physics experiments at the European Organization for Nuclear Research, or CERN, or CERN, at Geneva, and as well as the Duchess Electron and Synchrotron, or DESY, at Hamburg. And lately, he has been contributing at KM3Net, which is the international collaboration preparing the new generation underwater neutrino telescope, which is to be deployed in the Mediterranean Sea. He is also active in establishing a novel acoustic detector for ultra-high energy extragalactic neutrinos, as well as he has been active in educational and outreach activities and has supervised 8 PhDs in these, also being the author of numerous research papers. Now, I would also like to welcome our students and the parents, as without their support, the interaction which we are here today for wouldn't be possible at all. The journey with the students so far has been very exciting, and our educators always put their best efforts to guide and help in showcasing the hidden qualities of the universe. Bright faces that I see here today, envisaging their talents, will be citizens of tomorrow. They may tomorrow grow up to be Einsteins, Rabindranaths, Gandhis, or even Abdul Kalams, or even the next Dr. Christos, which we have here today. All right. As all of you know, today's topic is all about neutrinos. So, before we begin, what are neutrinos? Well, neutrinos are fundamental particles, meaning one of the types of the tiny particles that make up everything. In fact, neutrinos are the most abundant particles with mass in the universe. Like, if you hold your thumb in front of you, obviously, and blink, almost 100 billion neutrinos will pass through your thumbnail in that time. So neutrinos, they also come within the Earth's core. Our sun, explosion of the far-off stars, as well as the Big Bang, the reactions when the particles interact in our atmosphere, or even from reactions in our own body. Even bananas produce neutrinos. So, how was neutrinos basically discovered? What happened that in year 1956, Clyde Cohen and Frederick Reines experimentally discovered the neutrino in a reactor experiment. And even though neutrinos, as I have already mentioned, they are fundamental building blocks of the universe, we don't know much about them, so much so that we don't know how much they weigh or why do they have mass at all. So now, without wasting any more time, let us begin and unfold the knowledge that awaits. I hope you all enjoy the evening while Dr. Christos spreads the magic by sharing his great experience and research work about neutrinos. Knowing that all of you must be very curious and excited to know more about neutrinos, the doubts you come across meanwhile the interaction is going on, you can always ask in the comment section. I would also like the students and parents to wait for 5 minutes after this whole interaction gets over, as some vital information needs to be shared. So, Dr. Christos, before we begin, I would like to ask you, how did you find your interest in astrophysics or more so in neutrinos? Over to you. Hello. Hello, doctor. Can you hear me?
Now I can hear you.
Okay, so basically what I asked is, before we begin, I would like to ask that how did you find your interest in astrophysics or more so in neutrinos?
Okay, first of all, let me thank you for this honor to invite me here to talk to you and interact with all these students. I'm sorry, I cannot hear you at all.
Hello, am I audible now, Dr. Christos?
Yes, I can hear you now. Can you hear me?
Yes, I can hear you clearly. So you can continue.
All right.
Okay.
Right. So, first of all, I would like to thank you for your invitation. It's really a pleasure to be here today. My interest in neutrinos, I'm really an experimental particle physicist. I've been working in various experiments at CERN and DESI in the past, and at some point it became clear that one of the missing blocks, missing questions, if you like, on particle physics is connected, is related to neutrinos. So at that point, it was really a matter of finding new ways to explore this and study this issue. And a very interesting topic emerged. It has been building up in the last, 10, 20 years in the field of neutrino astronomy. It's a different kind of astrophysics. It's a new kind of astronomy. It's, as you will see from the title of my presentation, a new way to look at the universe. So
indeed is, Dr. Christos. But seeing you here today, it really intrigues me that what were you like in the early days? Like during college or even in school, you were always interested in astrophysics?
Yes and no. I mean, the universe always holds a special place in the minds of people who want to do, follow physics or related subjects. I mean, the universe is a magical place, as I will hope to convince you. I'm pretty sure that you know this already, but I would like to also give my own thoughts about this. It always had a really special place in my imagination and my thoughts. So yeah, it's been a long-standing dream, if you like, to be able to really participate in this adventure.
I agree. The universe always finds to show our path, to show us what path do we need to follow. I totally agree with that. Okay, so now this KM3Net project, which you are currently working on, for the development of the new generation underwater neutrino telescope. So what can we expect from it? What results do you expect to see, and how would it benefit us, should I say?
Well, this is, as I will show you in my presentation, this is a new kind of astronomy. It has some unique advantages in terms of what we can study. Astronomy is really a study of the universe. You can approach it in different ways. Your instruments can be of different technologies, and you can address different places in the universe. So you can do astronomy of the sun, which is close. You can do astronomy of the most distant galaxies, which are very far away. The whole, or anything in between, of course. But irrespective of what one wants to study, the basic question is to understand the universe, how we came about, how it started, and where it's going. Now, with neutrinos, we will have the opportunity to study questions that cannot be addressed with other ways of doing astronomy, with other technologies, other ways of studying the universe, like where do the cosmic rays come from, how are particles accelerated in the universe, things like that, which I will explain later, why neutrinos are possible to give us some information about, and why we cannot do it with other ways of studying the universe. We will be able to study the place where the actual interactions happen, so the interior of objects like stars and galaxies, and not just the surface, if you like. But I will explain this, I hope, in a more clear way during my presentation.
I am sure that you will be spreading magic around here to all of the viewers which are right now present with us for this interaction, and everyone would get to know about more of these fundamental building blocks called neutrinos, and basically why they are called the fundamental building blocks of the universe. So over to you, Dr. Christos. I am sure that you have great things planned for us in your presentation. So let's move on to it, and over to you.
Okay, thank you. I will share my screen now.
Okay.
Second. Can you?
All right. So everyone, I'm sure we will give Dr. Christos just a second, and here we are presenting, starting with our presentation, where Dr. Christos will explain how things function in our universe. As you can see right here written, a new eye to the universe. So let us jump into it and see what this beautiful interaction has to offer. All right, over to you, Dr. Christos.
So thank you again. So I will be talking about neutrino astronomy, a new eye to the universe. So there are two keywords here, neutrino astronomy. So I will be talking a little bit about astronomy in the first place. I hope that I will not bore you too much. Then I will briefly talk about neutrinos, and then about astronomy with neutrinos. So essentially what we're talking about when we're talking about astronomy is this magical place that we call the sky. The sky, which during the night, if you're lucky to live outside a big city with lots of light, can be something spectacular like this. And it's obvious that in the ancient times, not many large cities existed, not much light existed in these cities anyway. So all ancient civilizations, as you probably know, try to explain in various ways what these magic blinking lights in the sky are. And of course, they used different ways to approach this, either through religious beliefs or myths or stories. Some even tried in a semi-scientific attempt to contribute to the explanation of what these things in the sky, in the night sky, are. However, if we talk about modern astronomy starts in the 15th century, and it starts magically with four great people, four giants of science: Nicolaus Copernicus, Johann Kepler, and Galileo Galilei. These are the first three. Copernicus reintroduced the heliocentric system in the minds of the people. Kepler was fortunate enough to work with Tycho Brahe, an astronomer in Prague, who had the ability to be very meticulous in his measurements, and then that allowed Kepler to be able to formulate through the Tycho Brahe's observations to formulate the laws of motion of the planets. And of course, Galileo Galilei made a huge contribution through his observations. I will come back to Galileo a little bit later, but the fourth guy joining this super team of giants is, of course, Isaac Newton, who not only formulated the law of gravity as we know it, but at the same time, he devised and used for the first time mathematical ways of calculating what we call calculus today. In some form or another was the invention of Newton, and it was essentially the very first time that a lot of mathematical tools were used to calculate and predict what the objects in the sky are doing. Now, before I go on, I would like to make a short historical detour, and I would like to show you very briefly 7 historical moments in the history of astronomy. And I'm doing this because at the end of these 7 historical recaps, I would like to make a statement about astronomy, and I hope that by that time I will have convinced you that this statement is true. Now, I will start with Galileo. Galileo was the first guy who took one of these small telescopes that the captains in the ships used to navigate and turned it to see the objects in the sky. And for the first time, he observed the satellites of Jupiter, the craters of the Moon, the phases of Venus, rings of Saturn, sunspots, etc. And in one go, he really expanded our knowledge about what these magic lights in the sky are. I'm fast forwarding a few centuries to the 20th century, and in 1925, in Mount Wilson in the United States, the first observations with the then largest telescope on Earth were made. It was the 100-inch telescope. On that telescope, a then young astrophysicist called Edwin Hubble worked, and he wanted to study what was known at that time as nebulae. Nebulae were sort of something cloudy, a region in the sky with no discernible structure, something like a cloud. That's where the word nebula comes from anyway. And it so happened that with the observational discrimination of that telescope, Hubble was for the first time able to show that these nebulae were not really clouds. They were full of stars, and actually most of them were in large distances from our own galaxy. So in one go, the size of the universe expanded tremendously. Up to that point, we knew about our galaxy, we knew about our neighborhood. We could not imagine that we're only one of many billions of galaxies in the universe. So in one go, the field of extragalactic astronomy started, and as you probably know, Hubble was also responsible for the famous Hubble law, the expansion of the universe, and so on. Third case, a little bit later, in the States again, it was the first moments that the first steps, if you like, of radio broadcasts. People did not have TVs at that moment. They were relying on radio broadcasts to listen to the news and so on. But the technology at the time was very, very primitive, so the quality of these broadcasts was not very good. So in the Bell Labs, one of the topics of the day was how to improve the quality of these radio broadcasts, and Karl Jansky, a young electrical engineer, had built an antenna, which you can see on the right-hand side. It's a rotating antenna, trying to understand how he could make the quality of the reception and the broadcast better in radio broadcasts. And to his amazement, he detected signals in the radio coming from outside Earth, from space, actually from outside our galaxy, and that was the discovery of what we call radio galaxy. Radio astronomy, as we know today, started at that time. Fourth case, a few years afterwards, in 1964, Penzias and Wilson, you probably know their famous horn antenna. They were trying to study the ionosphere with microwaves, and instead they discovered in one go the cosmic background radiation, which is a radiation which exists everywhere in the universe, and is essentially the relic of the era a few thousand years after the Big Bang, at the time when matter and radiation decoupled. Fifth case, a few years later in Cambridge in the UK, Tony Hewish and his student Jocelyn Bell, they were trying to study interplanetary scintillation using a radio telescope, and instead they discovered pulsars, one of the most amazing objects in the universe. Even now, they are full of wonders. Sixth case, again in the 60s, in the height of the Cold War between America and Russia, the Americans decided to put up in the sky around the Earth some spy satellites. They called them Vela, and they were meant to detect possible nuclear reaction, nuclear explosion tests by the Soviets. Instead of that, they discovered that they had a series of signals in gamma rays coming from outside the Earth, from space, actually from the very deep space, and that was the signature of what we call today gamma ray bursts, or GRBs. They are one of the most intriguing phenomena, objects in the sky. They're full of unanswered questions, and they are usually mergers between neutron stars, but also other possibilities exist. They are extremely violent explosions. To give you an idea, within a few seconds, they can produce the amount of energy that is emitted by a whole galaxy. So they're really, really huge. Fortunately, so far they've been happening very far away from us. Finally, the seventh case, an experiment in Japan in the 80s, designed to detect proton decay. Essentially, a large tank filled with very pure water inside a very deep mine detected not, instead of detecting the proton decay, they detected solar neutrinos coming from the sun, and the corresponding solar neutrino problem. In other words, the amount of different kinds of neutrinos expected was not what was observed, and this gave this gave rise to a solution which had to do with neutrino oscillations, and therefore the discovery that neutrinos are not massless but have a finite mass, albeit a small one. And of course, the observation in 1987 of the first neutrino signals from the supernova 1987A. This is an image of the interior of this huge tank. It's full of photomultipliers. These round things are very sensitive detectors, able to detect singlet photons. You can see a small boat with some technicians repairing something or another, and of course in normal operation all this is filled with water. It's dark and doesn't have technicians or boats in, or small boats in. Finally, just to give you an idea, this is the image of supernova 1987A, and also an image of the sun with neutrinos, all taken with Kamiokande in the late 80s. Now, this is the end of my historical tour, and I'm recapping this. I'm putting this slide, which says essentially the same thing as I did so far, because the statement I want to make is the following. There is a pattern here, and I could have gone and showed you many more of these examples, but I think 7 is more than enough. There's a common pattern here, which has to do with the following. Each time that we use a different type of telescope to study something related to the universe, we end up finding out, discovering something different, something unimaginable, something extremely interesting. And this is the magic of astronomy and astrophysics. Because, you see, if you think about it, we're really talking about something, observing something which is very far away from us. It's not an experiment. It's not something that you can take it in your laboratory and play with it. It's not an accelerator. It's not anything. It's something that we can only observe from far away, and we don't have any means of interacting with it. So we're just sitting here, and if we're clever enough to observe it in special ways, then we can observe and find out things which are unexpected. We don't really know what we're going to find out or what we're going to observe in any study of the universe. So you see, visible light, Galileo and Hubble, the telescopes were used for navigation or to study nebulae, and they found amazing things about our solar system. They discovered that galaxies exist outside our galaxy. The universe is expanding all the time, and so on. Radio galaxies with radio emissions with Jansky, instead of studying noise, he discovered radio galaxies, and so on and so forth. So what I'm trying to convey here is that every time our technology allows us to see the universe in a different way, then magic and interesting and fantastic things appear. So I would like you to keep this, and I would like to move to neutrinos now. Now, neutrinos are what we call leptons. They are fundamental particles. They are 3 kinds of neutrinos. Each one is coupled with a different particle. We have electron, the electron and its electron neutrino, muon and the muon neutrino, tau and the tau neutrino. Electron, muon, and tau, electrons you know about. Muons and taus are essentially cousins of electrons with a larger mass. So muons are much heavier than electrons. Taus are much heavier than muons and electrons, of course. And each one of them has its own neutrino. And leptons, all 6 of them, do not interact with the strong nuclear force. As you probably know, there are 4 basic fundamental forces in the universe: the electromagnetic force, the weak force, the strong force, and gravity. So leptons do not interact with the strong force, but they see the other 3. Of course, they see the other 3 under conditions. For instance, electrons have mass, they also have charge, so they can interact with electromagnetism, they can interact with gravity, and they can interact with the weak force. Neutrinos, however, all 3 of them do not have charge, so they cannot interact with electromagnetic force. They have extremely small masses, almost zero, but not exactly, so their interaction with gravity is very small. So the only force that they can feel, the only force through which they can interact is the weak interaction. And by its own name, the weak interaction is very weak. So neutrinos, interacting only with the weak interaction, interact very little with matter. What does it mean? It means that they can pass through matter very easily. In the same way that a piece of glass is transparent to light, ordinary matter is transparent to neutrinos. Now, when we say transparent, there's a slight key point that we should make here. If you look through a piece of glass outside your window, we say that the glass in your window is transparent to light. However, it's not completely transparent. You can always realize that there is something in front of you, even if it's glass. So if you imagine a piece of glass not being a few centimeters, 1 centimeter thick, as a normal window would be, but let's say 1 kilometer thick, then light would not pass through that piece of glass because it will slowly be absorbed in the same way that water absorbs light. So the same thing happens with neutrinos. When we say that they pass through matter, and indeed through every one of you and me as well, every second pass billions of neutrinos, we're not completely transparent. We're very transparent, but not zero. So there's always a finite probability that the neutrino will stop in its interaction with matter. This probability is very small, but it's finite. So what is good about neutrinos? Why do we want to do astronomy with neutrinos? You see, we have to start from the fact that when we talk about astronomy, we're essentially talking about astronomy with photons. Either it's the visible light or the infrared light or the radio waves or gamma rays or you name it, it's usually photon astronomy. But photons are absorbed by matter. So if you want to do astronomy with photons, what you essentially do, you study surfaces. When you see the sun, you see the surface of the sun. You don't see the interior of the sun, because the photons that are produced inside the sun are not able to go out of the sun. They are absorbed very, very shortly. And they are emitted again, but at the end of the day, those who are emitted only at the surface of the sun are visible to us. The same thing happens if you try to study galaxies. If you have a galaxy, you see the side of the galaxy that is towards us. You cannot see the stars which are behind other stars. Or if you have a cosmic dust cloud somewhere in between you and an object, a galaxy or a star, you cannot see it because it's behind. So when I'm repeating this, when we're talking about astronomy or photon astronomy, we're talking about astronomy of surfaces. We're not able to study what happens in the interior of an object. Neutrinos, on the other hand, because they can traverse matter very easily, they can be produced in the center of a supernova, for instance, and those neutrinos will be able to pass through the outer layers of the supernova and reach us, bringing us information of what happens in the inside. The neutrinos which are created in the center of the sun pass through the sun very easily, and they come to Kamiokande in Japan and tell us about the solar neutrino problem. The neutrinos which are created in the center of a galaxy can pass through the matter that is in front of them, in between us and the galaxy, and give us information on what is happening in the center of the galaxy. At the same time, neutrinos, as photons, have zero charge, which means that if I look somewhere and I see a neutrino or a photon coming from a certain place in the universe, in the sky, then I know that it has been emitted by an object which is at that direction. This is in contrast with with protons, who are essentially the mediators of what we call cosmic rays. And protons are emitted also in various astrophysical objects. However, since they have a positive charge, they get deflected by the magnetic fields which exist in between the galaxies. So in terms of doing real astronomy, pointing astronomy of sources with protons, it's not possible because we don't really know where they are coming from. So to summarize this slide, neutrinos have a unique advantage with respect to other ways of studying the universe because they have zero charge, so we know where they're coming from, and also they can pass through matter, which means that we can find out what is happening inside them. Now, what we would like to know with neutrinos, essentially what we would like to know with neutrinos is to essentially probe the interior of these objects, and at the same time find out about the mechanisms that produce cosmic rays, the mechanisms that accelerate particles in various phenomena like active galactic nuclei, supernovae, and so on. Neutrinos have a distinct place in our models on how these explosions, these phenomena happen, and how the mechanisms of accelerating particles happen in these objects. On the left-hand side here, I'm showing you the energy spectrum. This is energy on the bottom, and then this is expected number in some units. The crucial thing which I want to emphasize here is that the energy spectrum is huge that we expect the neutrinos to be following. This is the energy spectrum of cosmic rays, but it's essentially the same as we would expect from neutrinos as well. At the very, very high side of the spectrum is really the neutrinos coming from extragalactic sources like GRBs, galaxy mergers, and so on. On the left-hand side, on the lower part of the spectrum, is essentially the galactic sources, microquasars, pulsars, supernovae, and so on. So let's go back to neutrinos and their association with neutrino. How do we do neutrino astronomy? The problem here is that the advantage of neutrinos is also their disadvantage. Because, as we said, neutrinos pass through matter very easily, but in order to do astronomy, to detect a neutrino, we have to stop it somehow, and we have to see where it's coming from. So we have to detect it, and this is the problem. So in order to stop it, it's essentially the same idea when you put your eye under a telescope. Your eye stops the photons coming from a distant star. It goes through the telescope and it stops in your eye, and then as soon as it interacts with the nerve cells in your eye, then you know that you've seen something. Essentially, the same thing you want to do with neutrinos. You have to stop them somehow, and then you have to use a special kind of telescope. So now we come to the place where we describe how we will do neutrino astronomy. It's the same thing as if you want to stop a bullet from a gun. You cannot stop it with a piece of paper because the paper is very thin. It will go through very easily. But if you put a large block of wood, for instance, in front of your gun, then the bullet will stop. So it's essentially the same thing as putting a target. You want to put a large target, in front of our neutrinos or behind our telescope. And what is the largest target that we have in our vicinity? The largest target is Earth. Earth is a very large target, is a very large mass. So we would like our neutrinos to go through Earth, to pass through the Earth. And then some of them, because the their numbers are huge, really, really, really huge. Some of them will, if we're lucky, will stop very close to our telescope and we will be able to see them. So neutrinos coming so neutrino astronomy is special in the sense that we don't look at the sky, we look down to the Earth, through the Earth to the sky. So we're looking at the sky on the other side of the Earth. So in this picture, the gray thing is the rock, sort of an average of what the Earth is like. The dark blue is water, and the light blue is the atmosphere. It's not in scale, but never mind. So what happens? Let's assume that this orange thing here is our telescope. We're interested in neutrinos coming through the Earth towards our telescope, and we completely neglect whatever comes from above. Why? Because we don't know what they are, what these particles are. They can be muons, they can be protons, they can be neutrinos, they can be whatever. The only thing is that we cannot really separate them. We cannot know what they are. On the other hand, whatever comes from inside the Earth is something that we are certain that it's neutrinos, because nothing else can penetrate such a large mass and then come on the other side. So we completely block whatever comes from above and concentrate only what comes from down below. Now, what is water doing here? Water actually plays two roles. The first role is it acts as a filter. It blocks whatever comes from above. I will remind you let me go back a few slides here to this Kamiokande experiment in Japan. What the Japanese did, for a different reason, but the principle is the same, they wanted to put their very large water tank shielded from whatever comes from space. So they put it in a very deep mine, thousands meters below the surface, and the rock above the mine, above the barrel, worked as a filter. The same thing we're doing here, only that instead of using rock or a mine, we're using water. So the water above our telescope acts as a filter, and it blocks most of the particles coming from above. And of course, it allows particles coming from below. But water also plays a second role, which is very important. Because if we go now into what happens when a neutrino comes close to our telescope, you will see the following. This is the rock, i.e. the bottom of the sea, and this is water. For the moment, you can ignore these vertical lines. So what happens is a neutrino comes, it interacts with one of the particles in the rock, or this red thing can be inside the water, it doesn't matter. And if this neutrino is a muon neutrino, then a muon is emitted. It gets converted to a muon, and then the muon carries most of the energy of the neutrino. These neutrinos have a very large energy, which means that the muons also have a very large energy. And then a muon with a very large energy can move inside the water for a few kilometers, 2, 3, 4, 5 kilometers, depending on its energy. But listen now, what happens? You have a muon with a very large energy, which is almost relativistic. It almost moves with the speed of light in the vacuum. So it's 300,000 kilometers per second. And the muon moves in the water, which is a dense medium, and it accelerates. So the muon interacts with the water, giving some of its energy to the water in the form of light. So it radiates. This is the way that the muon starts to lose energy. So the muon moves very fast, and it emits light. But now this light moves slower than the muon, because inside the water we know that the velocity of light, the speed of light is c, the speed of light in vacuum, divided by the refractive index. which in seawater is something like 1.35. So the light emitted by the muon moves slower than the muon. And this is what we call Cherenkov light. This is an effect first calculated by a Russian physicist Cherenkov, who also got the Nobel Prize for this. And it's a special kind of radiation emitted at a certain angle. It's essentially the same thing that happens when you have a boat in the water. Because if you imagine a boat moving, normally in the water, when the boat moves, let's assume that at t equals 0, the boat is somewhere, and then after a second it moves a meter, okay, or whatever. Now, to move inside the water, the boat has to move some water from where it was before to where it goes afterwards. So it essentially radiates a wave. It sends a water wave out to the outside. But then the boat moves faster than the wave in the water. So it leaves behind the wave that it has generated. And this is what produces this typical angular, this cone, if you like, of waves going behind the boat. The interesting thing here is that this angle of this wave is depending only on the speed of the boat and the speed of the wave in the water, nothing else. It does not depend on the size of the boat or anything else. So if you have a tiny boat and a huge ship moving at the same speed, they will always produce the same angle here, the same angular cone of waves behind them. And essentially the same thing that happens with the muon. The muon is the boat. It moves very fast inside the water, and it emits light, which it leaves behind. And this is why there is a very specific angle, which in the case, as I said before, in the case of the water, it only depends on the speed of the muon, which is the speed of light in vacuum, c, and also the speed of light in the water, which is c over n. So essentially, it only depends on the refractive index of the water. So essentially, it's a one-dimensional, one-parametric quantity. This theta angle in the case of saline water, seawater, is something around 42 degrees. So this is the key concept of doing astronomy. We want a neutrino to come interact here or inside the water. We have the muon at very large energy moving inside the water. It accelerates, it produces this very, very characteristic radiation, which is called Cherenkov radiation. And then what do we do? This is our telescope. Our telescope is a series of detectors, series of devices which can find, which can detect this Cherenkov light. And if you detect this light and also measure its time, then from the different positions of these detectors, you can calculate. It's not very difficult calculation, but it's cumbersome. You can calculate where the muon comes from. So you can calculate the direction of the muon, which means that you can calculate the direction of the neutrino, because these two things, neutrino and muon, are almost moving at the same direction. Their differences is typically at the energies of the neutrinos is typically less than a tenth of a degree. So then you see, I can find the direction of the muon, I can find the direction of the neutrino, and then I can go back and see where this points to. And I hope that I will be able to identify this with, I don't know, a known galaxy, a known GRB, a known supernova, a known whatever, and do my astronomy, study that specific object. So what does it look like? It looks like this. This is an artist sketch of what a large telescope can be. These lines can extend for a few hundred meters. This is actually an image of what we're trying to build in Chem3Net in the Mediterranean. This is one part of it. Each little round thing here is one of these spheres, which is pressure resistant, and it has a lot of photomultipliers in it, 31 to be exact, and they are very sensitive devices able to find single photons. So this thing is sitting in the bottom of the sea. The distances are something like 40 meters in the vertical and 100 meters in the horizontal, and all this can make easily a footprint of around 1 square kilometer, and the height is around 800 meters, which is more or less a cubic kilometer. That's where the name of Chem3Net comes from. But this is not the only approach. The first efforts of this kind of astronomy was in Dumont in Hawaii. This stopped many years ago. It did not go through. In Russia, in Lake Baikal, the deepest lake in the world, is an ongoing effort, but it's not completed. And then the Americans had built something similar in the South Pole in Antarctica with a small detector called Amanda. Now, nowadays, all this is getting bigger. In the South Pole, Amanda has grown to what we call now IceCube. It's a very large collaboration. I will show you some pictures of it. And then in the Northern Hemisphere, in the Mediterranean, we're building Chem3Net. Chem3Net is located in 3 places. It's not in one place. It's located in the south of France, east of Sicily, and the southwest of Greece. And I will show you some more about this. But before going to Chem3Net, let me show you what IceCube looks like. This is the South Pole. This is the place where it all is installed. And this is a schematic of how this telescope in the South Pole has been done. They dig through the ice very long holes going down to 2,500 meters in ice. It's a huge hole. And then this is the image of a hole. Then they lower these round detectors, as I showed you before, these glass spheres, and then they pour some water on top of it. It gets frozen, then it stays there forever. And they detect neutrinos. They've been active for a few years now. And on the right, there's a sketch of one event, one neutrino going through their detector. The principle in ice is essentially the same as detecting neutrinos in the water. There's very few differences. The interesting thing about IceCube is that in the last few years they have detected some neutrinos of extremely large, extremely high energy, and this has caused a lot of interest, and we're looking forward to seeing more results. Now, going to why are we building another telescope of the same kind in the North Hemisphere? One has to realize the following, that these telescopes are not pointing telescopes, they're not moving telescopes. You cannot turn it to look at the sun or turn it to look at another object in the sky. They're sitting anchored on the Earth, and they can only see towards the center of the Earth. So in the South Pole, the field of view of the telescope is rather fixed in the sense that it's in the most southern part of the Earth, so it looks down, so it looks at the north part of the sun, and it's also sitting on the axis of rotation of the Earth, so it's not really moving too much. So if you want to see what IceCube is essentially saying, if you plot the sky in terms of galactic coordinates, this is the horizontal axis here is our own galaxy, then this is the field of view of IceCube. There are a few interesting sources, but the thing is that it's missing almost completely the galactic center, the center of our galaxy. And why are we mentioning this? Because the center of the galaxy, or the center of any galaxy, is essentially the place where we expect interesting things to happen. This is the place where stars are born. This is the place where a lot of interesting and violent phenomena happen. So essentially, we want another telescope in the northern hemisphere to be able to study this region of the sky, and of course do extragalactic astronomy as well at the same time. So this is the field of view of what our telescope will be, based in the Mediterranean. It's slightly different in terms of shape, because you see that we are moving around the Earth. I mean, the Earth rotates, so we're feeling the rotation of the Earth. So the places in the night sky where we don't always see them, and of course there's one part of the southern sky which is always visible. So essentially, these two fields of view are complementary. So one needs the other to fully understand and study what happens in the universe. So although these are two different telescopes, one can consider them to be complementary in terms of what they are actually able to see. So the KMT-Net collaboration, let's go back to what we are. We're essentially, we started as a European collaboration. You see most countries in Europe, but nowadays we're moving towards a more extended participation. We have Moroccan institutions, we have South Africa, South Africa, we have Australia. Actually, in this map, China is missing, who joined us lately. Maybe India will join us at some point. We also have Ecuador from Latin America. And this is a picture of a small subset of our people. It's like 1/4 of what we are in a meeting some time ago. And let's go back to how this telescope looks like. This is an artist's view of what it would look like. So there are little anchors in the sea bottom, and from them these strings come up towards the surface. The distances between these spheres, which are the building blocks of our detector, is something like 40 meters. So all this, the height is something like 800 meters. If you imagine that this goes to a depth, the seafloor is at a depth of around 3,000 meters, then that means that on the topmost detector, on top of it, there's something like 2,000 meters of seawater acting as a filter. So, of course, this picture is a little bit misleading because it's not down there, it's not bright at all, it's very dark. It's absolutely no light comes from the surface. This is an artist's view, of course, of what a very energetic neutrino would look like. The color code here is essentially the timestamp on who comes first, and the size of the spheres is representing the energy of the photons that we detect. And you can see that this is a picture, a depiction, if you like, of the muon track that comes through with the cone, the Cherenkov cone, and then all the cycles that we can expect. What is happening now? We're building these lines. This is a picture of a vertical line equipped with these detection units. We call them digital optical modules. They are built in our labs, and we're slowly, gradually building up our detectors. So far, we have 6 of these lines in France and 3 of them in Italy, and we're building all these, all the time and putting them out to the sea. The way that we deploy them is we wrap up all this structure into an aluminum frame. It goes down to the sea, and then we unfurl it. It's like letting it unwind, because it has a positive buoyancy, and then this comes to the surface, and then the rest is left there. You can actually see this procedure in several videos that you can you can watch on YouTube. I will show you where to find them. And this is almost my almost last slide. In the near future, we hope that very shortly we'll be able to study new, interesting, and possibly unexpected phenomena, giving us the possibility to understand better the universe. This is our website where you can start exploring, and videos and images, more images you can see there, as well as several publications that we have so far. And I would like to finish with this picture. This is again a picture or many pictures of our universe in galactic coordinates, like the one I showed you before. The difference between them is simply the fact that these are the pictures of the same thing seen by different wavelengths of light. So this is the visible light on the bottom left-hand side corner. On top of it is the infrared, radio, atomic hydrogen, molecular hydrogen, near infrared, and so on, gamma rays, and so on and so forth. So you can see that the image, the picture that the universe presents to us. I'm coming back to this idea of having a new eye to the universe. Each different way of looking at the universe is unique and very different than any other. It gives us a lot of different information, different insights, different data on what is happening. And we hope that at some point, not in the very distant future, we'll be able here in the middle to put another picture, which will be the image of the universe with neutrinos. So thank you very much for watching me.
All right, so Dr. Christos, that was indeed great, and that was some brilliant information shared to us by your expertise, filled with information telling us how much is still left for us as humans to explore and find out about this universe. I'm sure each and every one of you who was present here during this interaction, as I can say for myself, I am truly delighted. So I am sure that all of you would have enjoyed it too. Being a part of this beautiful interaction, gaining so much information about the fundamental particles of the universe itself. Now, moving ahead, I'm sure Dr. Christos will be delighted to answer the questions from our students, as a lot of them have already shown keen interest in neutrinos, and obviously they want their doubts to be cleared. So, coming to the first question, as I will stick to it in one specific order. So, Shilpa asks that what is the difference between muon and neutrinos?
Okay. So if we go back to, let me go back to my slide.
Okay.
Can you see my screen?
I can see you, doctor. I cannot see you presenting right now. Okay.
Right.
All right, Shilpa. So your answer will be coming up in a second as Dr. Christos shares his presentation once again. Here we go.
Right. So you can see this slide now about leptons.
Yeah, yes, sir. I can. Doctor, I can.
Fine. Okay. So an electron, you know about. Electrons are building blocks of matter. They are in atoms. They go around the nucleus and so on. Now, a muon is something very similar to an electron, but it has a very large mass. So it's compared to an electron. So it's another fundamental particle of the universe, of nature, as well as this tau particle. So you can imagine muons and taus to be very close to what an electron is. only their masses are much larger. Okay? They all have negative charge, they have the same spin, they interact in the same way, and so on. Now, in addition of electron, muons, and taus, we have the neutrinos. Only that each of these particles, electron, muon, and tau, has its own neutrino, if you like. So we have an electron neutrino, a muon neutrino, and a tau neutrino. And what happens is that when a muon, one thing that I did not say is that muon and taus are not stable particles. So they don't really exist forever. When a muon is created, then after a while it decays, it gives us something else. So, and taus, the same thing. So when muons decay, then they always give us a muon neutrino. When electrons interact, they give us an electron neutrino. When taus interact, they give us a tau neutrino. And these are different particles. These are not the same. They're neutrinos, all three of them, but they're different kinds of neutrinos. So to answer the question in short, electron, muon, and tau are essentially the leptons with a significant mass and negative charge. Neutrinos are the leptons with zero electric charge and essentially no mass, or very small mass, to be exact.
Okay, so I'm sure Shilpa, your doubt got cleared. Moving on, we have Bhuvi Gupta from Ryan International School. He asks that what took you to the Cubic Kilometre Neutrino Telescope? So basically what your motivation was.
If I understand the question correctly, why do we need a neutrino cubic kilometer neutrino?
Doctor, the question says that what took you to the telescope? Like, why did you become interested to go to this?
Okay. The thing is, you can do neutrino physics in various ways. Neutrinos in accelerators are a little bit difficult to do, simply because neutrinos are notoriously difficult to produce and study. At the same time, this idea of doing astronomy with neutrinos, I combine both the physics of particle physics with the study of the universe, was something which was very intriguing. And at the same time, it's very interesting to realize that in the Mediterranean Sea, we have very deep waters, something that is not really known. We have waters that go down to 3, 4, 5,000 meters of sea depth. And the interesting thing is that the waters are very clean and also very close to the shore, which means that you don't really need a large cable to connect the place where the very deep water exists and the shore, which means that it makes our life easier. Okay, so the combination of having in our vicinity, in our neighborhood, very deep, clean waters close to the sea was a very interesting and intriguing coincidence to start this idea and go on to get involved and interested in a project like this.
Okay, so the next question is from Akshay VR from KR Mangalam Word School. He asks that how are neutrinos related to the formation of the universe or the cosmological inflation theory?
Okay, so inflation is a big story. Essentially, inflation. Neutrinos, as the rest of the matter, was essentially all intertwined, if you like, at the beginning of at the beginning of the universe. The interesting thing about neutrinos is after they decoupled from radiation, matter and radiation. Okay, and what is really interesting for us is that the non-zero mass of the neutrinos can play a significant role into the ideas of universe expansion and how we're going to, at the end of the day, relate the ideas, the models, and the theories of inflation with what happens at the moment. There's very little knowledge at the moment of these ideas, these concepts. It's very hard to how can I say it, make predictions or find out experimentally or observationally about the truth. So it has to be in a roundabout way our knowledge of what their relation is going to be, essentially plugging in, relating observational phenomena, observations which essentially link the later stage of the universe creation with what happened before.
Okay.
So we have a very long way to go in order to be able to answer questions like this.
Indeed, doctor. All right. So the next question is from Pratyush from Indraprasth International School. He asks, like, even he must be intrigued like I am, that what benefits would be getting out of the discovery of these neutrinos?
Let me ask you, why do you want to do astronomy? I mean, what is the benefit of doing astronomy?
The stars and everything intrigues me.
Right. So, this is the reason I'm asking this is because this can be thought of as part of a long-standing series of arguments on why do we want to do various kinds of science. And indeed, it is especially here in Europe, but I'm pretty sure that it has been happening all over the world. There are various ways of looking at basic science. Normally, applied science, i.e., part of science and research, which can end up very obviously into something that benefits society or benefits the end user or benefits you and me and our parents and our children, is something that is good, right? Because you make some research and then you make a new medicine, and this is obviously great. Or you make a new mobile phone or 5G or whatever, and again, it's great. Now, the question is, why would you do basic science? Because it's not evident always how to connect the usually large amounts of money required to do this basic science with a benefit. So why would we benefit by studying neutrinos? It's obviously not a direct answer. There are various ways to approach this question, and one obvious thing is to say, well, I have a curiosity, I want to learn, I want to study, I want to, there's a natural curiosity about things in our universe, in our lives, how it got started and all that. So this is the basic driving force. At the same time, one should realize that all these different ways of studying, and it's not only in astronomy and astrophysics, it's everywhere in basic science. Why would you do mathematics? Why would you study, something abstract? Apart from the natural scientific curiosity, you never know what will come at the end. And this is a gamble, if you like. Society will have to trust the people who are doing this kind of science that at the end of the day, something worthwhile, something good will come out. It does not happen always. Not everything has a positive outcome, but very often, and it's not very, very, very rare, something really spectacular comes out of this. And I'm pretty sure that you know that at CERN, for instance, in Geneva, the World Wide Web was born.
Yep.
Right. I can tell you that at that time I was working at CERN, and we've been using. It was not called www at the moment. At the time, we've been using it instead of email, and that's how it started. I mean, we've been using it to transfer files and texts from one colleague to another, and of course nowadays it's. We've been talking to the web now, and it's something very different.
Even when Nicholas Copernicus, he gave his theory, people were like that, okay, what good will come out of this theory? But later on we realized that, okay, that is one of the best theories we ever had. So I'm sure that something good will always come out if we keep on experimenting on new things and finding out more and more about our universe. All right. So, Doctor, the next question comes from Vidya from DAV Public School. She asked that what is the effect of neutrino in space?
I'm not really sure that I understand the question.
She asked,
what is the effect?
How are neutrinos like in space, basically?
How neutrinos
Basically, how neutrinos are up there in space?
How? They just travel in the same way that light travels everywhere. Okay, so you can imagine that there are neutrinos flowing around, traveling around at the speed of light, or pretty much the speed of light, because they have a very small mass, but they are everywhere. They just travel. And the sources of these neutrinos, where they come from, is what we want to find. We know that neutrinos exist in huge quantities, in huge numbers in the sky. And it's exactly their sources that we want to identify and see whether we can study them and make get information and insights and more information from this.
Okay, Dr. Markou. Moving on, we have a question from Gagan from Prudence School. He asked that why is spin momentum, basically what is a spin momentum and how is it related to a neutrino?
What is spin?
Spin momentum.
Well, spin, spin is a funny concept. It's it comes. You can imagine it as something coming from. It's like the angular momentum. Okay, but it's not really angular momentum because it very much looks like it, but it's a quantum quantity. So it's slightly more tricky. The thing that I can explain in plain words is that it's one of these quantities that are preserved in the same way that in an interaction you preserve the electric charge, for instance. Electric charge does not disappear. Spin is also one of these quantities that more or less follows the same rule. It is a quantity that we have to take into account when trying to calculate what interactions are possible and what are not possible. There's a whole series of phenomena that are related to spin. Polarization is also very closely related to spin. If you think about polarized light, this essentially comes from concepts which are very closely related to spin. But it's really a quantum concept, and it's characteristic of every single fundamental particle. Every single fundamental particle has a definite spin associated with it.
Okay. So the next question, which is I should say, a rather interesting one. Manas asks from Bal Bharati School that he has seen recent studies showing that when research devices was recently sent to the poles, like the ice cube, okay, they observed that neutrinos are being generated from within the earth, whereas neutrinos generally come from space to earth. So what does this mean? He wants to know that.
No. Neutrinos can be generated anywhere. I mean, you said that bananas produce neutrinos. I mean,
Doctor, I know. I'm just asking his question.
Right. So what happens is that neutrinos are produced everywhere. There are various ways of producing neutrinos through the weak interactions. It's typically a process called beta decay. It's very closely related to radioactive to the decay of radioactive isotopes. You have them in most processes which involve radioactive decays, and they're everywhere. Radioactive isotopes are everywhere. So neutrinos are produced in the interior of the Earth, in the interior of the Sun, anywhere. However, what happens is that typically the neutrino energies produced by these processes are much smaller than the energies of the neutrinos produced in, let's say, a gamma ray burst in space, which means, or in the Sun, which means that it's more difficult to detect them because their energies are tiny. So the effect is very small, but it's a legitimate source of neutrinos. They are produced inside the Earth in various processes, and it's nothing strange about this.
Okay. So the next question comes from Dev from St. Thomas School. He asks that, do you think there is a relation between disappearance of antimatter with neutrinos?
Okay. Well, this is one of the big mysteries. I really don't know. If I had an answer like this, then I would,
I agree.
Yeah. That would be. I would be more than happy to have an answer. That would be a huge breakthrough. Actually, this mystery of the disappearance of antimatter is a huge question.
That is indeed a huge question, and I am sure a lot of research and experiments need to be done. And let's just hope in a few years we get the answer to that.
Let's hope so. Definitely, I don't have an answer to this.
Okay, no problem, Dr. Markou. It's only obvious. We are still experimenting and researching. All right. So, next question comes from Dhruv from Bal Bharati School. He asks, what do you think about the string theory and a word with more than 3 dimensions?
What I think about string theory and what? And the rest I did not understand.
Basically a word with more than 3 dimensions. Because basically string theory says that there are 10 dimensions in the word, right?
Yeah. Well, you see, this is one hot topic because indeed string theory was started extremely promising and is still on the table by far. The problem with string theory is that so far we don't really know how to pinpoint and identify those aspects of the various models, because there's not, there's not one string theory. It's not one thing. The parameters that you can use, the symmetry groups that you can have, are very. Their number is great. Is a lot. It's very large, which means that in order to be able to identify and reduce the uncertainty in what could be a viable model of our universe, it needs a huge effort. So the point is that string theory is certainly one of the possibilities, but we don't really have any means at the moment to test whether any of the key predictions of a certain set of string theories is valid. One thing which is maybe interesting and people who've been waiting for is for the LHC experiments at CERN to confirm or not the existence of supersymmetry, because that would be the first step from the our existing knowledge of the standard model of fundamental forces and particles to a generalization of this the generalization. Unfortunately for us, up to now, doesn't seem that supersymmetry is giving us any signs of existence. But of course, we still have a long way to go until the new upgrade of CERN detector and the accelerator and the experiments happens in a few years' time. So we have to wait a little bit for this. But at the moment, we don't really have a way to really probe in an experimental way the existence or not of, or the validity or not of string theory. So it's something that is decoupled from our experimental possibilities. And I'm insisting on this because physics is really an experimental science at heart. I mean, theory has been a key, a very important part of physics. And of course, when one learns physics, one learns it in a way that has been filtered, if you like. So the stuff that you learn at school and the stuff that you will learn in university is a logical sequence of various theories and results. But this is not the way that research is done. Research is done through an interplay of theory and experiment. So things are not that clear. I mean, if you open a book on physics, any book on physics, it looks as if it's a very clear and logically concise subject. But of course, discovery can come in various ways, and it's not a straight line. So we need the confirmation, and then we have to go back in the theory. So string theory for the moment is our way of our current capabilities, and it will, unfortunately, I think it will remain like this for a long time.
Okay, Dr. Markou. So Tahir Rabidin, he's asking from a long time. So he's asking this, that why is the discovery of Higgs boson one of the greatest discovery in human history?
Oh, well, I don't know if it's one of the greatest discoveries in human history. It's been. You see, you have to put it in a correct context. I think, in the sense that it was a missing link in what we call the standard model. So it was a key concept which had to be there, because otherwise we would have to revise a lot of things in our theory for the fundamental particles, possibly in ways that we would not be able to understand how to do it. So the Higgs boson had to be there, if you like. It had to be there in the sense that it was the most logical thing. And the thing, you have to realize that the Higgs boson has been searched for a very long time at lower energies, and the intellectual challenge to find it and complete this puzzle was huge. Now, it's not clear to me whether the next, if you like, for me, supersymmetry would be a much greater discovery, simply because supersymmetry can be there or cannot be there. But if it is there, then supersymmetry is going to be a huge breakthrough. The Higgs boson was very important, but in a sense, we knew that it had to be there.
Okay, so Dr. Markou, just one more question. Anirudh Musad asks that why do neutrinos basically have no mass? What?
I don't know. No one knows. No one knows. I mean, these are questions that unfortunately we cannot answer, and we don't even know how to pose how to start answering them. So, for instance, why electrons have the mass that they have? Why protons have the mass they have? Why W and Z bosons have the mass they have? We know parts of the mechanism, and the Higgs boson is really helping us understand a little bit more of what is happening. But the real question of why the mass of the neutrino is a few eV is something that we have no clue on how to answer.
Okay, so similar to this, there's just another question asked by Adik Behel, that what makes neutrinos so inactive compared to other subatomic particles?
Oh, that's easy to understand, because you see, as we said, or maybe I think I said it, but anyway, there are four fundamental forces in the universe. So one is electromagnetism, the weak interaction, the strong interaction, and gravity. Some of them we have a common way of dealing. So, for instance, unified theories, the electromagnetism, weak force, and strong force are unified in terms of a common way of describing them. But let's, for the moment, stick to the idea that we have four different forces. Now, out of the four forces, leptons and of course neutrinos, because they are leptons as well, do not interact with the strong force. The strong force is the force that, for instance, creates and builds protons or neutrons. So it's really the hadrons, what we call the matter that is composed out of quarks. So this is the strong force, and leptons do not feel it. So electrons and muons and taus and neutrinos, by definition, if you like, do not feel the strong force. So one force is neutrinos do not have electric charge, so the charge is zero. So they cannot feel the effect of the electromagnetic force, because you need the charge to either feel the Coulomb force or a magnetic force or whatever. And of course, their mass is very, very small, almost zero, not exactly zero, but almost zero. Yes. So gravity does not play a role with them. So what is left is essentially the weak interaction, but the weak interaction is very weak. So the neutrinos, being these particles that feel only the weak interaction force, are by definition interacting very little. In contrast, if you think about it, an electron has an electric charge, which means that it will feel the electromagnetic force, and the electromagnetic force is much larger in strength than the weak interaction force. So it makes life very hard for the electron to penetrate, let's say, the matter. The photons have also zero charge. They don't interact with gravity or anything else. But then the photons are the particles which transmit the electromagnetic force. So they are like they are what we call the mediators of the electromagnetic force, and this is why they interact with the. I mean, they carry the electromagnetic force, so they interact with matter, and this is why they are absorbed away. So neutrinos in this respect are special because they only feel the one force which is very weak.
Okay. Okay. So, Dr. Markou, just one more thing. If you have, I would like to ask, if you have some more time, could we ask a few more questions, or is it okay right now?
If it's a few more questions, then I will be glad to answer them.
Okay, great. That's great, Dr. Markou. So, coming to the next question, basically from Manvik Sood from St. Columbus. So, he wants to know that, okay, I'm sure another one of questions which need far more experimentation to be answered. He wants to know that how are neutrinos emitted from the Earth? And is there anything smaller than a neutrino?
Sorry, the first part I did not hear.
The first part was how are neutrinos emitted from the Earth?
Neutrinos are emitted when a radioactive isotope decays, for instance. Okay, so you know that most elements in natural elements have a series of isotopes which are radioactive, are stable. Some isotopes are stable and some of them are not, and these are what we call unstable isotopes, radioactive isotopes. Okay, so then those isotopes which essentially have a finite lifetime, then they can transform to something else, and it is this process that can produce neutrinos in some cases. Okay, so this is essentially the whole story. So those isotopes in the Earth who are not stable produce neutrinos, and the energies characteristic in these decays are the energies of the neutrinos. What is interesting to realize is that this thing is there's a separate activity, a separate scientific activity, which is essentially a methodology of taking what we would call an X-ray of Earth using neutrinos. So you can study what the Earth is composed of by studying how the neutrinos are absorbed, emitted and absorbed inside the Earth. And this is an activity which uses techniques from like the ones I described to you to study the Earth, the various parts of the Earth through the existence and the detection of neutrinos.
Okay, so Dr. Markou, I'll be asking just final two questions, after which we will be concluding this wonderful interaction. And to be very honest from my side, I'm clearly loving it, as you can see it on my face. Okay, so Rita Patel asks that, is it possible that neutrino can interact with other neutrinos? And if yes, how?
No, you need a special kind of interaction, which needs. Well, yes, you can, but it's extremely difficult. I mean, in theory, you can have it, but we have not detected it ever. You can have a neutrino scattering through a Z boson, but yeah, it's not something that we can study essentially.
Okay, so Vibhav asks from Ryan International School, what is the difference between quarks, leptons, and neutrinos?
Quarks, leptons, and neutrinos. Okay, neutrinos are leptons. Okay, so leptons are this category of particles which contain electrons, muons, and taus, and they are neutrinos. So these are the leptons. Now the quarks are a different category of particles, and they are those particles which make up ordinary matter, the protons and the neutrons that are inside the atom nuclei are made of quarks. So our current understanding is that, for instance, a proton, and there are 6 kinds of quarks: up and down, charm and strange, bottom and top. So these again are organized in pairs in the same way, more or less, that the leptons are organized in pairs. So we have again, in the case of quarks, 6 quarks organized in 3 pairs, like the 6 leptons organized in 3 pairs. The quarks inside the proton are confined inside the proton. They are glued in the proton, if you like, through some other particles called gluons. And these are pretty much, they play the same role that photons, let's say, play in the case of transmitting the electromagnetic force. They transmit the strong nuclear force, and the gluons bind the quarks inside the proton, for instance, or a neutron. Our current understanding is that we cannot have free quarks, so we can always see them as inside larger, in quotes, particles, more complex particles like a proton or a neutron or a meson or whatever. So quarks are building blocks of matter, but we don't really see them by themselves. We always see them inside some other particle.
Okay, so that was great, Dr. Markou. And as for the students, I know there were a lot of questions. There were so many questions, but due to the shortage of time, we will not be able to take all of the questions. Okay, but what I do know for sure that all of you enjoyed the interaction, as I can say for myself that I loved the interaction throughout, along with all the knowledge I grasped, and I hope Dr. Christos cleared all your doubts. Okay. Now, Dr. Christos, I cannot thank you enough for taking out your precious time and giving us this part of your life where you shared all your views and research, enlightening us on this beautiful topic of neutrinos. I can proudly say that if gaining more and more knowledge makes us better humans, then me, along with all of us who were there for this session, I am sure after this interaction, they can also proudly say that we came out as better human beings. I would like to end this interaction with a statement said by one of the most brilliant minds we have ever seen. And since we have one of the most brilliant minds with us right now here today as well, I would like to say this quote by Sir Isaac Newton, that what we know is a drop, what we do not know is an ocean. So thank you everyone for being part of this beautiful interaction, and thank you Dr. Christos for making all of this possible and worth every second.
I would like to thank you for inviting me. It was really a pleasure interacting with you and all the students. Thank you very, very much, and I hope all